Good morning, respected sir. Today I'll be presenting my transport phenomena assignment. In this, I have, in this in this presentations, I will be explaining four different types of problem, which are plain fluid flow with moving wall, viscous heating in ballpoint pen, temperature rise in electrical wire, and forced convection between parallel plates. I will explain each problem step by step, including physical meaning, derivations, and numerical problems. First problem: laminar slit flow with moving plane wall, plane Couette flow, which is an extension of problem 2.b4, in which allowing the wall x equals to b to move in positive z direction at steady speed of v naught. And here we need to obtain shear stress distribution, velocity distribution. So in this problem, we will consider uh, wall at here x equals to 0, this minus b, and this 2 plus b. So this wall is stationary, and this wall is moving with v naught in positive z direction. So our main objective is to find shear stress distribution and velocity distribution of this plate. Before mathematics, let's understand the physics. If both plates were stationary, then only Poisson flow would occur because of pressure difference. But here, both are here one plate is stationary and other is moving with v naught velocity. So therefore, a Couette flow is also occurring, and as pressure difference also exists, both Poisson and Couette flow exist simultaneously. So here we will see how we will solve the question. So we will assume a steady state flow as property do not change with time. Flow is laminar. Velocity exists only in z direction. Now we will solve shell balance derivation. So what shell balance says? Rate of momentum in convective transport minus rate of momentum out by convective transport plus rate of momentum in transport in momentum transport, rate of momentum out by momentum transport plus force of gravitational or any other forces, external forces, should be 0. Here we will uh, we will take the dimension as a small fluid between this. So x will be x to delta x. In y direction, width will be dimensions will be 0 to w, and in z direction 0 to l. Uh, and coordinate system, we are taking Cartesian coordinates. As we know, velocity in x direction and y direction are zero. That's why flux of xx, flux of xyx, and flux yy are zero. So we will only deal with flux in z directions. So here, as we have taken the flux into area in xz direction and zz direction. Why not in yz direction? Because in that velocity of y is zero. So it will get cancel out. So we get del phi of xz by del x plus del phi of zz by del z is equals to rho z in z direction. Now we will do force balance in z direction. So first pressure force at z and dz direction. Then we will take pz of a, pz plus delta z is equals to minus dp by dz into a. Then shear force. Force act on the surface is equals to shear force. Tau xz by a into a minus tau xz into x plus dx minus is equals to minus tau xz by dx differentiate. And now we will sum of all the forces should be equal as the forces are balanced in this question. So now we will integrate minus dp by dz plus c1 with the help with respect to dx. We will integrate with respect to dx and we will get this. dp by dz is basically delta p by l, and here c1, if both walls were stationary, this this c1 would have been 0, but as one wall is moving and the symmetry is destroyed, so therefore c1 will not be equals to 0. So now we will be using Newton's law of viscosity to find tau xz, which will be minus mu dvz by dx. This relates with shear stress velocity gradient. Now we will substitute tau xz, which will help us to find in C1. Now we will integrate. We get Vz is equals to half dp by dz x square C1 by mu plus C2. Now we will apply boundary condition. As we know, one wall at x equals to minus b, Vz is equals to 0, and x equals to plus b, Vz is equals to v naught. By applying boundary condition 1 and 2, we get this equation and this equation. Now we will subtract these equations to get C1 and C2. So now C1 is equals to minus mu V naught by 2B, and C2 is equals to half mu dP by dz into B square by V naught by 2. Now we will substitute this C1 and C2 in the previous Vz equation. From that we will get this equation, which is final equation for velocity. And then now we need to find shear stress equation, which was tau xz minus dp by dz right plus c1, which, and after substituting c1 we get shear stress equation to this. And here of the of the velocity equation, this b square minus x square shows it's a parabolic because of pressure difference profile, and this shows linear because of wall moving. So basically this shows Poisson, and this shows Couette flow. With the help of this model or this type of question, we can predict drag force and energy consumption in the flow or materials element. Now, for problem 2, viscous heating in ballpoint. Here we are asked for the to check ink viscosity, why ink viscosity decreases. Does it decreases due to shear thinning or temperature thinning? Shear thinning is decrease in viscosity because of non-Newtonian effect, and temperature thinning is decrease in viscosity because temperature rise caused by viscous heating. If the temperature rise is less than 1 Kelvin, then it is due to temperature thinning, and then it is not due to temperature thinning, it is due to shear thinning. First, as we can see, the clearance of the ball and plates are very small, so we can consider this as a flat plate also, because the length the um, moving of flowing fluid is very small, so for our convenience we will consider this as a flat plate. And as we can see, from one place fluid is going and another place is stationary, and both the plates have same temperature as both lies in outside surrounding. Now, because of clearance be less very small, then our curvature is neglected and cylindrical flow becomes parallel flow, as we have explained earlier. So for the Cartesian coordinate system, we are considering Cartesian coordinate. X is equals to x plus delta x, z direction is equals to 0 से L, and y is equals to 0 से W. And for boundary condition, as I have told, x equals to 0, temperature is T naught, and x equals to B, temperature is T only. So now we will do shell energy balance. We will do a derivation through cell energy balance using total energy flux. Heat conduction plus mechanical energy transfer is equals to Q plus tau into Vx. Uh, Now we will integrate Ex as del dx by dex by dx is equals to 0, almost 0, because of very small clearance length, and so therefore Ex is equals to C1 first. And now we will apply Fourier's law. Qx is equals to minus k dt by dx. Velocity is the Vz is function of x only. Now, for Newtonian fluid, tau xz is equals to minus mu dvz into dx. So therefore, tau into v into x is equals to mu vz into dvx. From this to this. Now total energy flux is equals to Ex is equals to minus k dt by dx minus mu vz and dvz by dx. Since Ex is equals to c1, so from that we now get the constant c1. And for the ball motion, we need velocity as a function. As we know, velocity as a function of z. Velocity is a function of x, so we will consider Vz of x is equals to Vv x by v. So at velocity gradient, Vv by v as Vz dvz by dx is equals to Vv by v. So now substituting dvz by dx in the previous equation, I'm getting minus k dt by dx mu x Vv square by v equals to c1. And rearranging this, so after integrating we get tx is equals to minus mu 2k vv square x square minus c1 by kx plus c2. Both surface at temperature T0 and and then applying boundary condition to get T1 and C1 and C2. First we get at x equals to C2 as T0, and after applying the second boundary condition we get C1 as minus mu Vv square by 2v. Now we will substituting the formula and with differentiating dt by dx we will get maximum temperature at maximum temperature will be attained at x by b equals to 0.5. So therefore now as we have to solve the question for maximum temperature rise, we need to find the rise in temperature to find if it is if the decrease in viscosity is due to temperature thinning or not. So we will see the what is the maximum temperature elevation we are getting from numerical. From the question we know these are the uh, uh, these are the viscosity, velocity and k um, coefficients, temperature thermal coefficient that we know it is given in the question. So T minus T naught max is equals to mu Vv square upon 8k. After putting x by b equals to 0.5, we get this. So delta T max is equals to mu Vv square 8 into a 8 into thermal coefficient. So delta T max is 0.011 Kelvin, which is very less than 1 Kelvin. So therefore we can say temperature thinning is negligible. Of so decrease in viscosity is due to shear thinning and non-Newtonian behavior. And now for problem 3. Here we can see copper wire carries a current causing which causes electrical heating. and heat is removed by air convection as it is not having any insulation. So we have to find, goal is to find maximum temperature. For this, these are the data given in the questions. Uh, for the shell energy balance on the cylindrical cell, we say heat in minus heat out plus generation. Uh, Heat generation is basically SE sigma into E dash ka square. So SE is the generation we need. So radial conduction will be QR minus K dt by dr. Area which we will be applying is equal to 2 pi RL, which is this area. Heat flow, now heat flow as in heat in plus generation, we get it as 1 by R d by dr RK dt by dr, where SC is volumetric heat generation. For constant K, as K is constant, we can take it out and this will be the new equation form. Now first we will integrate with respect to R. So we will get, first we will get this equation C1 by R as we, and second again we will integrate, so we will get TR as SC by 4K plus C2, where C1, when we are applying a boundary condition, we see R equals to 0, C1 is equals to 0, dt by dr is equals to minus SC by R into K. Let R equals to R, we get C2. Uh, we will apply minus K dt Ts minus T infinity. Dt by dr we know from the previous slides, it is SCR by 2. So from there we get SCR by 2 is equals to H of Ts minus T infinity. We don't know the Ts value, but we know the T infinity value, it is given in the question. So we have to replace Ts by T infinity in every places. So T max is equals to C2. So Ts will be equals to T max minus SCR square by 4K, and T max is equal, we will put Ts at this place. So from there we get T max minus T infinity SCR square by 4K into SCR by 2H. Now we will be solving numerical part as we have derived the formula for the maximum temperature. First we need to find SC, which is sigma into E dash. So we get this SC, and from after putting SC in the formula, and we get T max as first term for the SC by 4K, SCR square by 4K, we get 1.6 into 10 raised to power minus 4, which is very small, and term 2 as in 0.77 Kelvin. So temperature elevation, if we say it's all matlab, temperature difference is almost 0.77 K, which is very small. So maximum temperature we will get is 27.77 degrees Celsius. So because of wire, we are getting 1.6 into 10 raised to power minus 4 Kelvin of temperature increase. And like with air, it's 0.77 Kelvin of temperature. So air temperature drop is 10 to the power 4 times larger than the heat conduction through electrics. Now the last question, force convection by heat. Fluid flows between In this question, fluid flows between two parallel plates receiving constant heat flux. Initially, temperature is uniform, and we determine temperature field downstream. We have to determine the temperature field at downstream. To make shell energy, here we need to make shell energy balance equation with respect to Txz, then discharge, viscous dissipation. Now, for the velocity, first we will take two infinite parallel plates separated by distance 2b. Flow of direction is z direction. Plate from minus x to plus b. Here are some assumptions. Fluid properties are constant. Flow condition, laminar fluid temperature initially uniform. Now the boundary condition. At entrance Tx x comma 0 is equals to T1, and wa- at walls heat flux, which is plus at x equals to plus minus v minus k dt by dx will be same is equals to q naught because of symmetrical condition, and because as heating is same in the both walls, so dt by dx equals to 0 at x equals to 0, because here we can see q naught will cancel each other. Now for the velocity profile, Vz is equals to as we know, for laminar flow, Vz is generally Vz max into 1 minus x square by v square. Now for shell energy balance, we will take small elements. Like x for x, we will take delta x, for z delta z. For x, we will take small element of x and small element of z also. And then we will see how the energy balance will happen. Energy in is equals to energy out. Energy in minus energy out is plus generation should be 0. So for convective energy flux, we have rho Cp Vz. Mu phi is viscous dissipation. So therefore, and mu phi is equals to 0, and dz d2z upon dt square is also equals to 0. For after that, the equation will be rho Cp Vz x dt by dz is equals to k d2t by dx square. After substituting velocity, we will get this equation. Now for dimensionless formulation, we get theta is equals to t minus t1 into q naught b by k, as it forms as theta is dimensionless. For coordinate x equals to x by v, x by b, which is both in meter, so it's cancel out. It is also dimensionless. And for sigma, we will also get the dimension. So for this derivation, we will get dt by dx is equals to d theta by 1 by b d pi. And then again we will differentiate it. We will get q dot by kb d2 pi, and also in z direction we will do the same thing. From that we will get t1 is equals to q naught b by k theta. After differentiating uh, and after differentiating we get this. Now using chain rule for d theta by dx, we will form the formula k rho cp vz max into b square. From that we will get dt by dz is equals to q naught rho cp vz max d theta by dt. Again we will do the same. First we will differentiate and take the derivative. This. Now we will put all this in the original equation, and we will get 1 minus x square is equals to 1 minus sigma square. So substituting at this point, we have 1 minus rho into. After substituting everything, we will get q naught by b into 1 minus sigma square d phi by dt. We have to derive theta with respect to sigma and tau. Here we will consider c naught t plus psi of sigma, and from there d theta by d naught is equals to c naught, and further we will take say with d2 sigma by d sigma square is d2 psi by d sigma square, and we will integrate with respect of sigma, and we will get c naught is into sigma cube by 3 plus c1. Now for the conclusion, from problem number 1, we get to know how momentum balance and boundary condition determines the velocity and shear stress distribution in viscous flow, and it shows how pressure driven flow and wall motion combines and create asymmetric velocity profiles. From question 2, we get to know the problem how the mechanical energy converts heat due to viscous friction in the fluid flow. From the third, we get to know how the heat generation inside the solids is due to electrical resistance and how heat removes by conduction and convection. It highlights that external convection resistance often controls temperature more than internal conduction. And from fourth, we get to know how energy balance predicts temperature development in flowing fluids. And it introduces us with the dimensionless of analysis to obtain universal temperature profile in thermally developed flow. Thank you.